going to work. Oh, all right, it's working. Computer is very erratic. Positive moment that we develop at C for a host of loads. First, there's a single concentrated live load of 8 kips, a uniform live load of 3 kips per foot, and then the beam has some weight, which is a dead load of 1 kip per foot. So the first thing we need to do is draw the influence line for this structure for the moment at C. So to help us visualize that, I'll redraw it with our fake hinge in the structure. We've got a pin at A and a roller at B. And remember, part of this Mueller-Breslau principle is that we act on the thing, which in this case, since we're looking for moment, we apply moment. So how would this structure behave? If this new hinge point, is it going to move down or up? It looks like it's going to move up. And when it does that, that would force the right side to seesaw and the left side to return back down to the pin. So there's the kind of qualitative assessment. So I'll go ahead and draw that, just so I'll have it formally. So I now have the moment at C. Now looks like this. So again, we'll have this section here seesawing over B, and this section coming back. And all these dimensions, as shown in the figure above, pretty short beam, just 4 feet. So we have to decide now we want to try to find this value or this value. I don't see any particular advantage to either. Which you want to try? You want to find the value at C or the value at the free end? C? Okay. So that means we have to now work a problem with our unit load at C. Again, that's mapping up to this value. And then we'll have reactions at A, AY, AX, and then over here at B, my reaction at B. And this has 4 feet, 4 feet, and 4 feet. Now remember, ultimately we're going to try to find the moment at C. So I'm going to end up also cutting the structure here. And when I do that, do I want to look at the left side or the right side? Yeah, the left side looks like it's going to be easier. So if I work the left side, I'm going to need to find AY. So my first step will be to find AY. To do that, probably the easiest thing to do would be to sum moments about B to solve for AY. So we'll do that. Most of you probably already know what our answer is going to be, but let's go ahead and check it out anyway. So about B, I have a positive moment produced by my unit load times a moment arm of 4 feet, and then AY creates negative moment times a moment arm of 8 feet. So it looks like AY is 1/2, right? So now let's actually draw that free body. I'll have to sneak it down here. So there's my structure with my reaction at A, 1/2. You could even consider the unit load to be there. And remember, we're trying to find this interior moment at C. So how do we do that? Sum moments at the cut. So if I sum moments at the cut, make sure I'm in equilibrium. I have the moment at C, that's positive with my sign convention, right-hand rule. This unit load creates no moment because it has really no moment arm. And then I have 1/2 creating negative moment with a moment arm of 4. So it looks like my moment at C is equal to 2. And that would be 2 feet, kind of an odd unit. So that means this value here is 2. So what should this negative value be? Well, positive 2 is to 4, as this is to 4. It's also 2. That would be negative 2. So there I have my influence line. So now using the influence line, again, let me draw a line here just to separate this work on the bottom. So using the influence line, let's solve the problem, which is the maximum positive moment at C. So the first one we'll look at are the live loads. Those are the ones that move around. So the concentrated live load is 8 kips. And we're looking for the maximum positive moment. So what's the maximum positive value on our curve? 2. So I'll have 8 kips times 2 feet, which will give me a contribution of 16 kip feet. That's the moment produced by the 8 kip load. Right? There it is, 8 kips. Now let's do the live uniform load. Where would I put the uniform load on this structure to create the maximum effect? Well, just under the areas that are positive. So I'd run it from 0 to 8. So in that case, I would have, let's see, the live load is 3 kips per foot. 3 kips per foot times the area of this positive part. It's a triangle, so 1/2 base, 8 feet, times height, 2 feet. So it looks like I get 24 kip feet. Did I do that right?
Yep.
And again, just to emphasize, that's the live section. Yeah.
From the right side.
Say that again?
Just on the right side.
The area that I computed is the area of the positive part of the curve.
Well, the whole thing.
What's that?
The whole thing.
That's dead load. That's the next one. So when I do dead load, I don't get to choose. Dead load is everywhere. In this case, dead load is 1 kip per foot. And now I have to take the area of the total curve. They're both triangles, so I'll have my 1/2 factor out front. Starting at the left side, it'll be 1/2 base times height, so that'll be 8 feet times a height of 2 feet. Then this segment here will have a base of 4 feet and a height of -2 feet. So what's that equal to? 4. So that's 4 kip feet. So the total for the maximum positive moment at C would be the sum of this stuff. It looks like 44. So 44 kip feet is the moment. And what's the configuration look like? So again, I'll come down here and quickly sketch the beam, which has a pin at A and a roller at B. So again, our dead load goes over the whole length of the structure, and that load has a value of 1 kip per foot. Our live load goes over just the first 8 feet of the structure. And that's an additional 3 kips per foot. And then where is our concentrated load? At C, which is right here in the middle. So that's the load configuration that produces the maximum positive moment at C. So any questions about that? This is a very doable test problem.
So for this one, do you want us to draw the picture, or can you just find?
I may not ask you this. I may just ask you what's the maximum moment at C. If you produce 44, you produce 44. I'm adding this so you can conceptually see what we're doing. Remember, too, if you have multiple segments that contribute, either positive or negative, depending on what you're looking for, you might have to start and stop the live load several times across the structure. You want all the positive areas for positive effect, or all the negative areas for negative effect. In this case, there's just one. Well, actually, you could think of it as two. But it could go positive, negative, then back positive. You'd still have to consider all the positive areas.
Is that with a concentrated live load?
The concentrated load, just one position.
I meant the...
Now, we could rework this problem, and I could ask you, what is the maximum negative moment? All right? Just for discussion, what would that be? Where would we put our 8 kip force to create the maximum negative moment at C? It would be here. And you can see, interestingly enough, for this problem, it's the same contribution, except it would be negative. Does the dead load change? No. So even though we're looking for maximum negative moment, it's going to make a positive contribution. The live load now would only be over this section of the beam. Mr. Isbell.
So would the maximum negative moment just be the same as or you just would you subtract anything?
No, you just would compute each of these and add them up.
Okay. But what
in this case, the dead load makes a positive contribution regardless.
Right. What would you subtract your live load from that if it's a negative number? You're adding it.
Well, you add them up. Whether they're positive or negative, you add them up.
Okay.
Okay. We'll stop here. If I can stop this.